What's up, everyone? This is our last section of Unit 7, 7.7, looking at some more trig equations. All of these equations we're going to be able to solve using factoring techniques or using other trigonometric identities, okay? So first example, we're going to solve this equation by factoring. 2 sine squared of x minus 3 sine of x plus 1 equal to 0. We're solving it only over the interval from 0 to 2 pi, okay? So this equation is already in what's considered quadratic form. That means I can factor it just like I would a regular quadratic equation, okay? So the factored form will become 2 sine of x minus 1 multiplied by sine of x minus 1. And you can double check that. If you were to multiply this back out, it'll take you back to 2 sine squared of x minus 3 sine of x plus 1, okay? Since the factors are being multiplied to equal 0, we can use a zero product property and say that each factor should equal 0. And then we're going to isolate sine of x in each one of these new equations and then solve for x. Okay, so sine of x equals 1/2 when x is pi over 6 in quadrant 1 or 5 pi over 6 in quadrant 2. And then sine of x equals 1 only at the quadrantal of pi over 2. So we end up with a total of 3 solutions for this equation. Okay. Second example, solve this equation using identities. Sine squared of x minus sine of x equals cosine squared of x. And once again, solving on the interval from 0 to 2 pi. Notice this equation has both the sine and cosine functions within it. I don't like that. I am going to use a Pythagorean identity on cosine squared of x so that I can rewrite it in terms of sine squared, okay? So I have sine squared of x minus sine of x. I'm going to keep that the same. And then again, cosine squared of x, I'm going to rewrite that as 1 minus sine squared of x using a Pythagorean identity. Now notice the equation is solely in terms of the sine function, okay? So from here, I would move everything to one side, get it set equal to 0. So I'm going to add sine squared of x to both sides. Those, of course, cancel out. And then I'm also going to subtract 1 from both sides. So that's going to lead me to 2 sine squared of x minus sine of x minus 1 is equal to 0. And now we're back in a quadratic form again. So this is factorable just like the previous example. We are going to factor to 2 sine of x plus 1 multiplied by sine of x minus 1. So you set each factor now equal to 0 and then isolate sine of x. So that's going to lead me to sine of x equals negative 1/2 this time, or sine of x is equal to 1. Sine of x would equal negative 1/2 down in quadrants 3 and 4. That would be at 7 pi over 6 and 11 pi over 6. And then, of course, sine of x equals 1 again at pi over 2. Okay. All right. Another example. Solve 2 sine of theta equals cosine of theta using identities. And this time we're solving in terms of degrees from 0 to 360 degrees. So similar to the last equation, I don't like the fact that I have both the sine and cosine function within this equation, all right? Anytime if I can use identities to rewrite the equation in terms of a single trig function, that's the approach that I want to take, okay? So there's multiple ways you can do that for this particular equation. One way would be to divide both sides right away by the cosine of theta. All right, so those will wipe out, or I'm sorry, these will wipe out. And then you can use a quotient identity here. 2 sine of theta over cosine of theta is the same as 2 times the tangent of theta. and that'll of course equal 1. Okay. Now I isolate tangent. Tangent of theta is equal to 1/2, where theta would either be in quadrant 1 or quadrant 3, since it's equal to a positive 1/2. Now let's draw out quadrant 1 here. Y is 1, x is 2. That's going to make r radical 5. That is not a special right triangle, so that's my indication I need an inverse tangent function here and my calculator, okay? So I'm going to find inverse tangent of 1/2. The calculator should give me the first quadrant angle, which is going to be approximately 26.6 degrees, okay? To get the third quadrant angle, simply take that 26.6 and treat it as a reference angle in the third quadrant. So you're going to add it to 180 then. So it gives me a second answer of 206.6 degrees. Okay. Now I mentioned there's other ways that we could have approached this equation. We could have squared both sides right off the bat. That would have given me 4 sine squared is equal to cosine squared. And then I could have changed cosine squared to 1 minus sine squared and then tried to proceed from there. But I think that would be a little bit more work than the approach we took in this case. All right, so I want to give you an opportunity to practice on your own here for a minute. Pause the video, work through the problems on practice 1 sheet here, and then come back and check your work with mine real quick. All right, moving forward into another example of an equation that can be solved using identities. We have sine of 2x multiplied by sine of x equaling cosine of x, and we're back to solving on the interval from 0 to 2 pi, so in terms of radians. This equation has both sine and cosine functions within it. That's not what I'm most concerned about. I'm most concerned about the fact that sine of 2x, its argument is not just x, okay? Instead it's 2x. So right off the bat, I can change that by using a double angle formula. Recall that sine of 2x is the same as 2 sine x cosine x, okay? And now all of the functions within the equation are having arguments of x, okay? So I like that now. 2 sine x cosine x, if you multiply that by sine x, we could rewrite this as 2 sine squared x cosine x, okay? And this time I actually don't mind that I have both sine and cosine functions in the equation, all right? Here's the approach I'll take. I'm going to set this equation equal to 0 by simply just subtracting cosine of x over to the left side, okay? And then my approach here is going to be recognizing there's a GCF of the cosine of x that can be factored out. If I pull that out, that's going to leave me with cosine of x times 2 sine squared x minus 1 equals 0. And now I can set each of those factors separately equal to 0. Okay. Now cosine of x equals 1 at 2 different quadrantals. Recall cosine is defined by the x coordinate of your point for your angle. So that's going to first happen up at pi over 2. And then it's going to happen again at 3 pi over 2. Okay, so right there are 2 solutions to this equation. And then 2 sine squared of x minus 1 equaling 0. Let's isolate sine squared of x first. So that's going to equal 1/2. And then you're going to need to take the square root of both sides of the equation. And be careful here. Recall when you take the square root, you need to consider positive and negative cases. So this is going to equal plus or minus 1 over the square root of 2. And that plus or minus allows our angle x to now be in all 4 quadrants. Okay, so let's just draw out quadrant 1, where y is 1, r is radical 2. That's going to make x 1 as well. So that's 45 degrees, or pi over 4, as your first quadrant solution. Treat that as a reference angle in the second quadrant. That's going to lead to 3 pi over 4. In the third quadrant, it would be 5 pi over 4. And in the fourth quadrant, 7 pi over 4. So notice we're ending up with a total of 6 solutions for this equation. Okay. All right, one final example. Directions here say to solve using a graphing utility. The equation 2 sine of theta equals cosine of theta plus 1. And again, solving it on the interval 0 to 2 pi. So sometimes we're presented with equations that we just can't solve by hand. Okay, there's no factoring or identities that will work to lead us to solutions completely by hand. Okay, and this is one of those equations, right? I'm not going to be able to do any factoring or use any identities here to make this work. Okay, so we'll solve this using Desmos. You could also do this on your graphing calculator as well. Let's open this up, and I'll simply just treat each side of the equation as its own function. Okay, so in box 1, I'm going to type in the equation y equals 2 sine of theta. Okay, and then in box 2, I'm going to type in y equals cosine of theta plus 1. All right, and I'm simply looking for the intersection of the two curves here, but only on the interval from 0 to 2 pi. So I'm going to go up to my wrench here, my settings. I'm going to make sure I'm in radian mode, and I'm going to change the x-axis to being from 0 to 2 pi. Okay, so now I'm only seeing the interval that I'm trying to solve over. And again, I'm looking for the x coordinates of these intersection points because the x coordinates represent the angle measures. Okay, so there's one solution at approximately 0.927, and then another solution is at exactly pi. Okay, so how about we just round? We're going to say x is approximately 0.927 and then at pi. All right, so your turn to practice once again. Try the 2 problems on the next sheet here, and pause the video as you do so, then come back, check your work with mine.